bias and the CB junction is reverse biased. Okay, now this actually figure shows that it's uh, connections and the biasing in the common base configuration. Okay, now there are the various kind of the currents flowing through this transistors, which we are going to see over here. Now here we can see that the I and E, okay, I small n and capital E, so it stands for the electron diffusion current uh, injected at the emitter base junction. Okay, what it is? Electron diffusion current injected at the emitter and the base junction, and the other current is the INC. What is it? What does it mean? That is the electron diffusion current reaching at the collector. Okay, this is the electron diffusion current reaching at the collector. Then there is a IRB. Okay, there is one more current which we call it as a IRB. Okay, so actually it is here, that is nothing but the IRB, and this current is actually equal to the nothing but the INE minus INC. Okay, so the difference between these two is actually it stands for IRB stands for the loss of the electron current recombining in the base. Okay, so the how much amount of the recombination happens in the base is given by the this IRB current. Okay, then the another terminal, that is the IPE. Okay, what it is? IPE, whole. P stands for the whole, so the current I is the current and is the diffusion current, so the whole diffusion current at the emitter, and obviously the other term is the base one, so the emitter base junction. Similarly we can have the IRE, so R stands for the recombination current, so that is IRE stands for the recombination current at the emitter base junction, and the one more current, that is ICO, that is a reverse current at the collector base junction. Reverse current at the collector and the base junction is given over here. So the basic operation of this transistor will be understood in the qualitative manner. Let's consider firstly the major current components, and the other components will be seen in the latter parts of this. When this emitter junction is a forward bias, okay, we are talking about the normal modes of the operation. Okay, so the when we are talking about the emitter base junction is forward bias, then the PN junction current consists of, so PN junction current consists of the electron and the hole currents, because we are talking about the PN junctions, and the both the majority as well as the magnetic carriers are contributing to the current. So the electrons are injected into the base, okay, and the diffuse through the base eventually, and this that will be collected by the collector, and does not okay, and uh, collected by the collector. So the base being the p type, okay, so it presents a barrier to the electrons, because it contains of the holes as a majority carriers, because it is a p type of the region. So it presents the barrier to the electrons and does not collect the any kind of the electrons, so there is no any collection of the electron in the base region. So the whole diffusion current on the other hand originated from the base and manifests itself as the base current and does not affect on the collector current. So this current does not affect on the collector current. So the now the ratio of this IC to the IB, okay, ratio of this IC to the IB is thus the electron to the whole diffusion ratio, okay, whole diffusion components of the base emitter junction. So however, if you look at the injection ratio of the electrons to the holes is a large, okay, because there are majority carriers as the electrons in the n region and the minority carriers are the holes. So if you just try to look at this injection ratio of the electrons to the holes is a large, such as the case of the it is considering like the n plus p kind of the emitter base junction, by virtue of which we can have the difference in the doping level, and this always we can have, if you just try to take the ratio of the IC by IB is always very greater than 1. Okay, IC by IB is always greater than 1. It can be easily realized. Now let's talk about the some static characteristics which are derived from the p-n junction theory. Okay, so now to illustrate the fundamental properties of the transistor, we here assume that the IV relationship of the uh, emitter and the collector junction, which is given by the ideal diode, that is Shockley equation. Okay, that is the effects due to the surface recombination generation, then the series resistance and the high level injections are neglected in this case. So these three things we must keep in mind. So some of the effects we will be considering in the latter as well. So let's try to understand the what are the its current properties. Okay, as we can see from this doping profiles and the critical dimensions of the abrupt impurity distributions diagram, we can see over here that all the potential drop across the junction depletion regions only. Okay, so the whatever the potential drops are at the depletion regions only. Okay, now in the neutral region, in the base, okay, neutral region, that is we are talking about the base region, uh, from which is starting from the x is equal to 0 to the x is equal to w. This is the width of the base region. Okay, so the injected minority carriers distribution, that is because for the base the electrons will be acting as its minority carriers. Okay, because it's a p region. So which is governed by the continuity equation, and that continuity equation is given by this. Okay, so what it is, 0 is equal to minus np 0 upon tau n plus dn d2pn by dx square. Now, so the general solution to this equation is given by the np of x is equal to np0 some constant. Okay, and then the c because this is second order differential equation, so we are having the two constant of the integration, that is c1 and c2. And here is the one more terminology is ln. Okay, ln is defined to be the diffusion length in the base region, so it is defined to be the is already defined, that is ln is equal to root of dn to n. Okay, now yeah, C1 and C2 are the dependent on this C1 and C2. Okay, this C1 and C2 are dependent on the boundary conditions, that boundary conditions of the NP of 0 and NP of W, means boundary condition which are there, x is equal to 0 and x is equal to W are the boundary conditions are imposed on it. So what is the C1 and C2? Okay, it is defined to be over here, so you can just try to read them by pausing the video. Okay, so c1 and c2 are defined to be here, and you can place over here. So this is a complete solution corresponding to it. Now the boundary conditions at the two edges of the neutral base regions are related to the junction biases. Okay, and this junction biases are given to be the np of 0. Okay, at x is equal to 0 we are trying to apply the boundary condition, that is npo exponential of q phi b upon kt. Why phi b over here? This is the potential difference applied across the emitter and the base. Okay, base emitter potential, which is to be the forward biased junction. Okay, so that's why we are having here the qvb. Then the on the other hand, if we just try to look at this place with the how much is the potential drop or the potential applied, that is nothing but the phi b c, because collector base voltage potential which we have applied over here. So the np at the x is equal to w is equal to npo into exponential of the q phi bc by kt. So with this boundary conditions, the electron distribution is known. Okay, electron distribution is known, as well as its diffusion current as well. Okay, its diffusion current. So the electron current at the emitter, okay, so the electron current at the emitter edge, that is INE, as well as the electron current at the collector edge, that is INC, can be defined. Okay, or which is given by the equation, that is nothing but the INE is equal to AE q dn d dnp by dx at x is equal to 0. So we are evaluating the differentiation at the x is equal to 0, okay, as the left boundary we can consider. Okay, so if just try to differentiate and substitute the value of the x is equal to 0, so we will get such a complicated equation, that is ae q dn np upon ln, and cot hyperbolic, and some exponential terms are there, but here the potential is vbe. Similarly, what we can have, the electron current at the collector edge can be defined to be the similar fashion, that is inc is equal to ae q dn dnp by dx at x is equal to 0. So the integration is evaluated at x is equal to w. Okay, now uh, okay, so the similarly we will get the another kind of the equation over here. Okay, so let's discuss a little more about the this kind of the equations here. Okay, so in normal modes, okay, so here, okay, so before we go for this, what is here, a is the cross sectional area of the emitter base junction. Okay, a is the uh, cross sectional area of the emitter base junction. So the electron currents are valid for the both the normal mode and the saturation mode. So let's talk about the in the normal mode. What a normal mode, in the sense that the vbc, so this junction has to be the reverse bias, and this junction has to be the forward bias. Okay, this is normal mode what we have, because we have seen in the operation modes of the transistor. And np of w, because we are talking about the right and boundary condition, or that is at x is equal to w. So np of w is equal to 0. So the current at this edge is ine, collector current is given by this equation. Okay, ine is equal to a q dn np upon ln cot hyperbolic w of ln exponential of qvb by kt. Okay, on the other hand, inc current is given, and here it is given by this equation, that is ae given, because we are talking about the vbc is less than 0. So whatever the we are talking about, the potential difference is the vbe only. So now if we just try to take the ratio of the inc by ine, okay, inc by ine means how much amount of the current is collected divided by the electron current at the emitter edge, and is called as the this ratio is called as the base transport factor. Okay, is called as the base transport uh, factor, and it's represented with the alpha t. So the difference of this ine and inc contributes to the part of the base current. So if you just try to take the difference between this, that is the contributes to the part of the base current. Okay, we can see the for the other condition, that if we just try to have the width of that region is very less than the diffusion length, then the ine, okay, in is very close to the inc. Okay, so in the case of the when w is very less than ln, then ine is approximately equal to inc. In the this small limiting case as w, this equation or the equation for the collector current and the uh, emitter current is almost equal, and is given by the a eq dn by npo upon w exponential of qvb by kt. But we can substitute the value of the npo 0 as ni square by nb. So this will result us into the alpha t is approximately equal to 1, because both are the same. Yes, this is the ratio, alpha t is equal to inc by ine. Okay, now uh, here in the other hand, if you just try to reduce in the simpler form, what we can say, ine is equal to inc is approximately equal to a into dn by qb by w square. What is qb? Qb is nothing but the injected excess charge in the base region, and it is given by the equation is nothing but the qb is equal to q times integration of the np of x minus np 0. This is the excessive charges. Okay, these are the excessive charges. It's originally and this is at the x is equal to some region in between the base, okay, into dx. So if we just try to solve this integration, what we will get it, that is q w np 0 upon 2 exponential of q vb by kt is the how much we can have the injected excess charge in the base region is given by this qb. Okay, on the other extremities, okay, on the other extremities means this is the case when w was very very small. So, okay, this was the case when w was very very small. So the small w, the condition which we have considered here is this one. Okay, now on the other hand, if we just can have the other boundary condition as something